talk about a couple of sort of vocabulary terms. We've run into them, at least the first one, before once. We didn't talk too much about it at that point, so we're going to talk just a little bit about this time, make sure everybody's clear as to what this is describing. So the first one on here is angle of elevation, and this is an angle measured from the horizontal line, or from the horizontal, we'll say it that way, up to the line of sight. And I am going to draw a picture of what that looks like, but before I draw the picture, I'm going to talk about the angle of depression, and I'm going to show you the relationship between the two. The angle of depression is an angle measured from the horizontal down to the line of sight. Okay, so the picture I want you to imagine is a football stadium. So some of you have probably been watching football on television because there's been a lot of it going on, right? So imagine that you have somebody who's up in the stands. I am not an artist by any stretch of the imagination. Okay, so there's my person, excuse me, up in the stands. And you've got someone down here on the field. Perhaps a player, maybe they're a coach, maybe they're a band member. I don't care. Okay. So there's one of them that has to look up to see the one person, and there's the other one that has to look down. Everybody with me? Now, if they were looking straight out from where they are, that would be the horizontal. So each of their horizontals are different places, right? So this guy, his horizontal, he has to look this direction, or at least he has to look, down here, and then this guy's horizontal's over here. So everybody with me? But if they're looking at one another, then their line of sight is right here. Okay, so the line of sight's what I'm drawing in red. Okay, the horizontal is what I drew in yellow. All right, so imagine what's going on then is that the angle of elevation is the guy on the bottom looking up. Okay, so his angle of elevation is right here. So this is the angle of elevation. It's from the horizontal up to the guy in the stands. All right. Now we have the guy up in the stands. He's higher up, right? And he has to look down. So right here is his angle of depression. There's a relationship between those two angles. They are the same angle, at least they're the same measure, right? Do you remember why?
Because it's parallel.
Yeah. These are two horizontal lines, and this is a set of parallel lines, right, because they're both horizontal. And in geometry, you talked about something way back when, it may have been a long time ago, that if you cut through a pair of parallel lines with what's called a transversal, it's just another line, that it creates alternate interior angles and they're congruent, or they're equal. So that's what's going on here. So when we talk about an angle of elevation and angle of depression, they are different angles, but they measure the same thing depending on which perspective you're looking from. Does that make sense? Okay, so we're going to take some examples with these, but I want you to understand that the relationship happens there. So, whoops, went the wrong way, I think. All right, I don't know what's happening. Give me just a second. All right, so we're going to take a couple of word problem examples and so show how those work. And I mentioned this last time, and I'll mention it again, is that solving the problems with the triangles is actually more work than the word problems, okay? Because you only have to find usually one thing with the word problems, or it's a multi-part problem, and it outlines for you as you go through which steps you need to do next. All right, so suppose that we have an angle of elevation of the sun, and that should have a degree on it. Let me put a degree there. Is 23.4 degrees. Okay, so we've got the sun, and here it is up here. That's my sun. I know it's the wrong color. And we'll go like that, and now it will be closer. All right, so there's the sun. And the sun is creating a shadow on a person. So we've got Diane Carr, and so Diane is down here. As you know, I do stick figures. So here's Diane. And when the sun shines on you at an angle, like when it's not right straight up, you know, highest in the sky, it creates shadows. You guys are aware of this, right? Yeah, that's good. Okay. All right, so the shadow that it creates does something like this. Okay, so wherever this little person is, and there's the horizontal for the person right here, I've got a shadow, and the shadow is right here on the ground. Okay, can you picture it? Does it make sense? Now it says the angle of elevation of the sun. Well, you can describe it however you want to describe it as far as your picture is concerned, but the angle of elevation of the sun is going to be this angle right here. Okay? You can talk about it being, they always call it angle of elevation of the sun. I don't know why. It would almost seem like it's an angle of depression, but the sun doesn't really look down, so I'm thinking that's probably why. The sun's not doing the looking, okay? It's shining. All right, so here's my angle of elevation right down here, and that's 23.4 degrees. And we've got Diane Carr, who's 5 feet 9 inches tall, so that's fairly tall for a young lady. But there's a problem with that from the get-go. I don't really want to write in 5 feet 9 inches tall. What's wrong?
You want to write in just inches?
Either in inches or in feet, one of the two, right? I don't want them to have this mixed notation. That's how we describe heights, and I get that, and that's fine. But it doesn't work very well for working with it in terms of mathematics. I'm going to go with, let's use a representation for feet, just because it works out nicely, and my numbers will be smaller if I leave it in feet. So what is 9 inches? I have 5 feet, and I have 9 inches. What is 9 inches in feet? It's 3/4. So it's 9 out of 12, right? And this is 3/4, or if you do it as a decimal, it is 0.75. So we end up with the height of this young lady right here being 5.75. That yellow is not so good, is it? I'll try not to write in it. All right, so I'm going to redraw this triangle because I need it just a little bit bigger for my liking. But I have a triangle. And, okay, it looks something like this. Right? I know that this side is 5.75 feet. I know my angle here is 23.4 degrees. And I'm asking for, or I'm sorry, it's asking me to find the length of the shadow, which is down here. So what relationship can I set up between those three pieces of information about this triangle? It is tangent. So tangent is opposite over adjacent. So the tangent angle is 23.4 degrees. And what will that equal? .75 over, what'd you call it? B? All right, we'll call our shadow B then. All right then, so I need to multiply by B because it's got to be out of the denominator. All right, so then I've got B tangent 23.4 degrees equals 5.75. Then what? They divide by the tangent value. So I'm going to divide by tangent of 23.4 degrees. All right, it's a mess over there, but pretend. Okay, so you're going to grab your calculator, and you're going to take 5.75 again, make sure you're in degrees, and hit the division button, and then divide by tangent of 23.4 degrees. And it doesn't indicate how many decimals I'm supposed to use, so how many am I going to use? 2. Okay. 13.29. Okay, do I have confirmation from others that we're getting? All right. Yeah. All right. So that's Diane's shadow. Any questions on that one? Okay, I have one more example. No shadows in this one. We've got an angle of inclination, which is not something I described with, I don't know, the other two angles that I just mentioned, but we can imagine very quickly what that means, right? It's an incline. So it's the angle that the incline is creating. It's the, okay. Don't know what the iPad's doing, but we've got my new screen. It's not going to look good probably online, but we'll see. All right, the angle of inclination from the base of John Hancock Center to the top of the main structure of the Sears Tower is approximately 10.3 degrees. If the main structure of the Sears Tower is 1452 feet tall, how far apart are the two skyscrapers? Assume the bases of the two buildings are at the same elevation. That's important, actually, information, because, of course, you know, if you were talking about something being up the hill from something else, this wouldn't work very well. So we've got two skyscrapers, and one of them, whoops, we'll do this. Here's one of them, and it doesn't actually even tell us which one's taller, but I'm pretty sure the Sears Tower is the one that's taller, right? Yes?
In our notes, it says 1451, so 1451, 1451.
Oh, I'll change it on here. It's just a typo somewhere, so it doesn't really matter. We'll go with 1451. Thank you, Micaiah. Does everything else match? Okay. All right, so we have two skyscrapers, and it says that the angle, so this one's the John Hancock one, and we're going to make this one the Sears Tower, because I'm pretty sure Sears Tower is taller, just from thinking about it, I'm pretty sure. So, okay. It says from the base of the John Hancock Tower, which is down here at the bottom, right here. Okay, I assume I was going to get a button. There we go. There's my base of my John Hancock Tower. Up to the top of the main part of the Sears Tower. So a lot of buildings, you know, have sort of antenna and things like that on top of it. They're just talking about the main part of that, okay? So this is the image that we've got. So from here to here, I've created an angle of inclination. Okay, I could have spaced them further apart, but I want to make sure I have enough space to work my problem out. And I've got my horizontal, right, which is down here as well. It doesn't look very horizontal, but pretend. All right, so this angle right here, which definitely does not look like 10.3 degrees, not drawn to scale. I told you I was no artist. This right here is my 10.3 degree angle. And I'm told, well, that I have the height of the Sears Tower, right? That's this piece right here. And after we fixed it so it matched what your notes said, I have 1451 feet. Okay, so do you see the triangle? And I don't have it labeled quite as such, and I can draw it again. So my triangle looks not at all like that. How about something like this? And I have 1451 over here, and I have 10.3 degrees. Pretend that's a 3. 10.3 degrees over here. Right? That looks terrible. All right, and I'm supposed to find what? How far apart they are, which is where in this picture? It's the value at the bottom. So you have to make sure you're answering the question that they asked, right? Because they could also be asking us how far is the base of this building to the top. They could be asking for, in essence, the hypotenuse, right? But that's not what they're asking for. So just be real aware of which problem's asking you to do what. All right, so the relationship between these three pieces of information, let's call this X, is tangent again, actually, yep. So we're going to have tangent of what? Of 10.3 degrees equals 1451 over B or X or whatever letter you pick, right? Now I'm going to do two things at the same time, just because we did a problem like this just a moment ago. The setup was the same. I'm going to multiply by x and divide by tangent 10.3. Okay? So this turns automatically into x equals 1451 over tangent 10.3. What do you get?
7,984.34.
Okay, I think I'm going to run out of space. Can you say it again for me, Erin?
7,984.34.
Feet? Yeah. Any questions? Do you agree? Did everybody get that value? Excellent.